Okay, so we end up discussing now the difference between the intrinsic and the extrinsic semiconductor. So some points to remember: before manufacturers can dope a semiconductor, they must produce it as a pure crystal. Okay, they must produce it as a pure crystal. Then afterwards, that's the time that they can add impurities by controlling the number of impurities to dope with the pure semiconductor. So in this manner, there is now the control of properties of semiconductor. Historically, pure germanium crystal were easier to produce than pure silicon crystal. And that's the reason why germanium was considered before. Okay? So that is the reason the earliest semiconductor devices were made of germanium, because of that one. So now we will now proceed with what happens when semiconductor now becomes extrinsic. So if it becomes extrinsic, as you remember, we had done increasing the number of electrons or increasing the number of holes. Okay, so increasing the number of electrons, we add pentavalent atoms. Adding a pentavalent atoms will create a free electrons. If you want to increase the number of holes, we add trivalent. And trivalent only has 3 valence electron. Therefore, there is a vacant space, creating extra hole or increasing the number of holes. So this time, let's now go deeper. We will discuss on the two types of extrinsic semiconductor. And that is the N-type and the P-type semiconductor. So in order for you to understand, let's have first a drawing of this one, no? Let's use the paint. So I will now be adding now the this discussion. So this is now our discussion. There are two types of extrinsic semiconductor. Okay? So the first one is this. So as you can see, if we add the number of if we have pentavalence, there are more electrons as compared with holes, no? So meaning to say, if there are more electrons as compared with the number of holes, so what we have now is we are increasing the number of electrons. So electrons is much more higher, okay, as compared with the holes. Okay, there. So if you remember, in an intrinsic, there is an equal number. And since we add, no, since we add, um, for this one, we are talking about N-type material. Since we add class, um, pentavalent atom, there is a free electron. So that's the reason why there is now an increased number of electrons. Okay? So meaning to say, if there is much number of electrons as compared with the holes, these electrons now is what is known as the majority carrier. Okay? So they carry the charge negative. Majority carrier. That's the reason why they were called majority carrier. Next, let's talk about the holes. Okay? When let's talk about the holes. For the holes, since free electrons is much more number as compared with the holes, so the holes now are called as the minority carrier. Okay? So with that, what happens now is we were able to increase the number of holes, increase number of electrons as compared with holes. So there are now two materials. Okay, we already have the two materials right now. So we have the materials with has a number of electrons. We call that one as the N-type material. Okay, so when we increase the number of holes, this time what we have now is the P-type material. So let's have the P-type material. So increasing the number of holes will have a P-type material. So what does a P-type material look like? The P-type material simply look like this. Okay? P-type material simply looks like So let's have a break. Okay, let me just copy na lang. So let's have this one. So the p-type material. Oops, what happened? And so for the p-type material, so as you recall, let's have a recall. The first type of extrinsic, we have the n-type material where there is an increased number of free electrons, or electrons is the majority carrier. How does it happen, no? When we added pentavalent atoms. Then the next one, when we added trivalent atoms, we create another type of material. We create a p-type material. Why? Because this time, what is the majority carrier is actually the whole. So the whole is the majority carrier. So if that will be the case, meaning, as you can see, there are a lot of holes, no? There are a lot of holes as compared with the electrons. So the number of holes is much more higher as compared with the number of electrons. So this type of material is what is known as the p-type material. So again, for extrinsic is a pure semiconductor. We add pentavalent to make an n-type. We add trivalent to make a p-type. The next question is, what happens when we combine the p and the n-type material? So that's the next question. So combining now the two materials, let's say this is now the p material and this is now the n material. As we all know that the p material, so let's write this is a p material. As we all know, this is now your p and this is now your n material. P material, the majority carriers are mostly electrons, okay? And usually holes for the p material. Okay, and for the n-type, the majority carriers are electrons. So we represent that one with negative symbol. Okay, so these are the majority carriers. Under p material, the minority carrier is the whole. Under p material, the minority is the electron, while under the n material, the minority is the whole. Okay, so what do we have? We have now, class, what is known as PN. We have now a PN layer. So this is what is known now as a PN layer. So it's a layer where the P and the material are actually combined. No, they are now combined, or they are simply attached to each other. So let's have some parts of this P and N. The center part. Okay, the center part, this is what is known as the junction. So this is what is known as the PN junction. Okay, so this is still a layer, PN junction. Now, this is actually the physical layer of a diode. So the figure above, so I'll say this is now your figure A. Figure 1 is the physical layer or physical structure of a diode. So that is already the physical structure of the diode. And next is, if I'm going to draw now the schematic diagram of the diode, you'll have like this. So you have a straight line, a vertical line, and let me go back. So you have a straight line, you have a triangle, okay, and then you have the bar, okay. So the bar represents the negative terminal because it is more of the electrons. So this is the negative terminal, and the triangle, this side is more of the positive because it has much more of a whole carrier. So that is the positive terminal. And what we have now is what is known as the schematic. This is now what is known as the schematic symbol. So this is what is known as the schematic symbol of a diode. Okay, so for figure number 2, so for figure figure 2, what we have now is the schematic symbol of a diode. Now that you have the physical structure, you have the schematic symbol. What is next is what is the how do you use this diode? So we go now to what is known as diode biasing. But before that, let us check first our lectures that we have. So here, p-type was already discussed, and then we have what is known as a p-layer, or this is actually the layer of a diode, and we call it as unbiased. It is called unbiased because we are not yet applying any voltage for the diode to operate. The layer in between the two material, this is the N material and the positive this is the P material, the circles are minority. No? Those symbols or those polarities that are encircled are actually the minority carrier. So this is the P material on your left side, and on your right side is the N material. So in between, we have the junction. Okay, so that's the word junction diode. It was also called as a junction diode. So it was called diode because it has two electrodes. Okay, the electron and the hole. So let us now move forward. Moving forward now, this is also known as the PN crystal. Moving forward, so something happens in between this layer. So we will discuss that one next video. On the next video. I think the time is already up for this one.